know a block joke.
That's nice, you can share, you're just gonna leave it in the blog.
Why should I share it?
Oh my gosh.
King of randomness spoken jazz.
Good. So our goal is to approximate solutions to differential equations. We can solve separable differential equations. We can solve if it's multiply, but we couldn't solve if it was add or subtract or something like that. So here I have a slope field. You just need the general idea of it in your notes. You don't have to be super exact.
Where's the funny not?
So the slope field is approximating, well, not approximating, sorry. The slope field is showing us what the solution would look like. I didn't even write the differential equation down for this, just a picture of a random slope field. What does it kind of look like our solution is going to be? If we kind of followed it along.
Oh, it looks like that one design on toothpaste.
Emma said probably around x cubed. It kind of looks like the solution would go something like that. But if it's a differential equation that we cannot solve for and we couldn't get the actual equation for this solution, we could still approximate a value if we knew some initial conditions. So let's say I know, let's put this on a coordinate system since it's not yet. Did you guys already draw a coordinate system or did you just draw the lines? Okay. So put your coordinate system about here. Again, it doesn't have to be super exact. You just need the general idea of what the slope field looks like. So if I know some initial conditions, if I know what's going on at some x and y value, I can approximate what's going on later in the equation. So let's say I know something about that x and y value. But what I really want to know is I want to know about something a little bit further on. It can't be too far away. It can only be a little bit further on. What can we always do with a curved function? Let me think of how to phrase this. Thinking of how to ask it so it doesn't sound super confusing.
We were just entertaining ourselves.
So even what's the easiest function for us to work with and to know things about?
A line.
A line.
A dot.
Okay. A line. A dot is not a function.
It is.
I guess you could do a piecewise function where it's only true for one value. So I could use a line at this point. What kind of lines do we usually end up drawing at? Tangent lines. So if I drew a tangent line here, where is the value of the tangent line going to be a pretty good approximation for the function itself?
Right on the line.
Okay. Right when they're meeting. If I go further out, if I try and use this to approximate my function, is that very close?
Not even close.
Not even close at all. So if I use my tangent line and I say I want to approximate something a little bit later on, not too far on, what if I want to get it even closer? So what if all I know is really this information and I don't know what's going on in the function later on? So if I only know what happens at that point we started with, what I could do is take a spot on my tangent line that I do know about and draw another line that will get me back closer on track and closer to the graph. If I did a second line, and this time I'm just going to do a short piece, it'll bring me a little bit closer to the graph than I was before. And if I take another small piece, and I could find stuff about my line, because it's easier to find stuff about lines. If I did another one and got even closer, I'd be getting closer and closer back to my graph. That's kind of the general idea of Euler's method. It's to find a tangent line and then keep finding lines that will get me closer and closer back to a better approximation on my graph. And where it's the most useful is actually in programming your calculators. Your calculators find the derivatives and stuff, the numerical derivatives. Usually, at least the old school, I don't know about the new school, usually they were programmed to follow Euler's method to get that approximate value. It's a very good programming tool. So, we're going to have to find a lot of information on this, and it's better to keep it organized, which is why I have my table. On my table, I think I have 6 spots for this one. I can't drag it up without using my mouse. So we are going to need to keep our information organized just so we don't get lost in the middle of the process. So if we have a differential equation, I cannot solve that. I could not find exactly what f of 3 is. I don't have enough information. But I do know f of 2 is 0. So I know for sure f of 2 is 0. But I don't know what f of 3 is, but I can approximate this. And this is how it'll ask a question like this. If we know some initial information, f of 2 is 0, use Euler's method with steps of 0.2 to approximate f of 3. So when they say steps of 0.2, that's our next value where we're trying to take a new line to get closer back to the graph. So when we do this, we're going to need to know what x is, we're going to need to know a slope, and we're going to need to know what y is. And I put y on the far right because that's what we're ultimately trying to find. We're trying to find f of 3, so we want to know what our y value is there. So what x value are we going to start at? What x value do we know information about y already? 2. We know what y is already when we're at 2. Actually, no, this, I'm trying to think of how it's set up again. No, yeah, that's where we want to put the y. So if they want steps of 0.2, that means my next x value I'm going to pick 2.2. I'm moving to the next x value on the list. I'm going to add 0.2 each time. That's what they mean by steps. And the more steps we use, the more accurate it would be. But when they have you do this by hand, usually they only have you do 2 steps. I did more on this one just to help practice and get the idea. So what will all the rest of ours be? Bless you. And we'd stop at 3 because that's what we're trying to find. So the x values we can get from the very beginning because with any function we usually choose x. Okay, so if we're finding a tangent line, what's the equation for our line? What's the equation for any line? Y equals mx plus b, but that's not the one we use in calculus more often.
y1 minus y equals m times parentheses x minus x.
Now since we're specifically trying to actually find y, I'm going to move y1 to the other side. So when we say m, what are we usually talking about when we say m? Slope. What else in this problem represents slope? dy dx. So really, when we're talking about m, and we're working with Euler's method, m is really dy dx. Good luck, Emma.
It's Good Friday tomorrow,
Bring
remember. Okay,
food.
your sister eat the cookies. Okay, all excited.
Okay, so I need to go back up for a second. So when we're finding a line, we usually find a line because we know 2 points on the line. So we know this points are x1, y1. Sorry, x1, y1. And we're trying to find this point here. But what do we know already about this point here? 3 is the final one. 3 is like all the way over here. Let's say we're just at the first step. Where is my first step located? 2.2. So this x value, we already know. But the y value we're trying to find. So when we're working with our equation, we already know that x is 2.2 and x1 is 2. We just don't know what y is. Well, what's going to happen when we have 2.4 minus 2.2 when we do our next one with these 2 points? If we do 2.2 minus 2, what are we going to get? 0.2. What about if we do 2.4 minus 2.2? 0.2. 2. This stays the same all the time. So we call this, because it's the same amount of change, delta x. Just so we don't have to keep plugging in to get the same answer over and over again, where delta x is our step. So delta x is the step they ask you to use. So now that we have this information, we can start filling out our table. So first, we need to find dy dx. Well, we already know what y is. So how would I find dy dx if I know what x and y are originally? Plug it into the dy dx equation, x plus y. So we know this whole thing is always going to be x plus y, so in this case, 2. So over to the side, for this first tangent line, we know y is 2 times, and then we know we always use delta x, so times what? 0.2 plus whatever y value we already know, 0. So that would give us 0.4? So that's our new y value. 0.4 is our new y value.
So then it's 2.2 plus 0.4 to find.
So now we're done with this point. We've used it for our purposes. Now we're trying to look at the next 2 points. So as Melinda said, 2.2 plus 0.4 is 2.6. So now we go and do the process again. Y is, this time dx, or dy dx is 2.6. The step never changes, that's always 0.2. Plus, but our y value now is 0.4. So at this point, we may want to plug it into a calculator instead of trying to do it in our heads. What did you get, Josh?
0.92.
0.92. So that's our new y value. And then we do it again. 2.4 plus 0.92 is 3.32. Again, after we're done with one complete row, it is not used anymore. You don't have to cross it out every time, just for emphasis, I've been crossing it out. So we do it again. Y is 3.32 times 0.2 plus 0.92. Evelyn, what did you get? 1.584. And I would use all the decimal places. Wrong spot. So we add those together again. 2.6 plus 1.584. 4.184. So we do again. dy dx is 4.184 times 0.2 plus 1.584. Anyone?
Oh, that's 2.4208.
This one?
Wait.
Oh, no, actually that makes
Yeah,
sense.
yeah, that one.
Okay.
2.4208.
208. I was looking at the slope column, that's why I got confused for a second. So we add them again.
It's 5.2208.
And then this is the last one we need. Y is 5.2208, and again I would use all your decimal places, plus 2.4208
Equals 3.46496.
So that's all we need,
Oh.
because that gets us to f of 3. F of 3 is approximately 3.465. Now we can round. It's semi-close. The further away from your original point, the further off your approximation will be. And the bigger your step, the further off your approximation will be. So it is just an approximation, but you can use it to help you find values that are close to values you already know. So on the AP test, if you had to do this by hand, they're only ever going to ask you to do 2 steps if you have to do it by hand, so you don't get that many decimals. If they did ask you on a calculator question, they probably would have more steps. On this, I did put more steps just to get the practice and the idea, kind of do some repetition. So let's try a problem with 5 equal steps. If y equals 3 when x equals 2, use Euler's method with 5 equal steps to approximate y when x is 1.5. So in this particular problem, they didn't actually tell you what step value to use. But using a little logic, we can figure it out fairly easily. Where did they tell us to start, and where did they tell us to finish? Start at 2, finish at 1.5. So that is a distance of 0.5 apart. If if we're doing 5 equal steps, what should we use for our step? 0.1. The last thing I want to point out before you get started on this try problem though is 2 to 1.5 is getting smaller. So instead of 0.1, it would be negative 0.1. So I'll give you about 3 minutes to solve this problem. So we know originally we have x is 2, y is 3. We find our slope using the new differential equation, 2x minus y. So our slope for the first one would be 1. So then we write out our tangent line. And that will give us sorry, wrong thing. 1 times, so 2.9. So our new y value, and we do already know that our x values are going down by 0.1 every time. So our next y value is 2.9. We do the process again. So I need my new slope. My new slope would be, and we're using this new x value of 1.9. We don't just keep using 2 over and over. 0.9. Hopefully that's looking familiar. So 0.9 times negative 0.1 plus 2.9 is 2.81. So then your next slope should be 0.79. And your next y value should be 2.731. So now I just want you to check and see where your answer may have gotten off, because it looks like it's just getting off by a little bit. The next slope would be 0.669. And if I'm not matching you two, let me know in case I make a mistake. So 0.669. Should give you 2.6641. This should give you 0.5359. So your final answer should be 2.611 or 10. You can truncate and still get full credit. So does everyone see where they may have made the tiny mistake? Okay. And there's so many steps going on, it's easy to mess up one of the steps as you're going. Okay. So the second section that we're going to talk about is in section 7.5. Again, we're taking the small portions of 2 different sections that wouldn't take up an entire day by themselves. It's called logistic growth. Logistic growth is a more accurate representation of population. Usually we use e to the x or ce to the kt. But if we think about real life, population doesn't get bigger forever. Usually when the population gets too big, either A, you run out of resources, or B, there's too many people, so you end up having some sort of plague. Something will limit your population. Or if you're talking about animals, maybe they have predators that limit their population. Lots of real life things that can actually affect your population and make it so it can only get so big.
Years.
Okay. So with these equations, they will not ask you to actually solve that particular differential equation. When you see the formula for it, it's kind of a beast. But you could solve it using partial fractions. Because the p's are representing our y values, we'd have to divide them over and they'd be on the bottom. We'd have to use partial fractions to solve this particular differential equation, which is one of the reasons we did learn partial fractions. But on the AP test, they won't actually make you solve this differential equation. Because again, it is kind of a pain. So the differential equation for logistic growth is dp over dt equals kp times m minus p. So notice, there are no x values in this differential equation. T is our x value, and there are no p's in this differential equation. So if we did one, let's say that dp dt is k, let's make it even simpler. Let's just say p times 7 minus p. Just for simplicity's sake, so we can get an idea of what the picture will look like. So if there are no x values involved in this, when I go to draw my slope field, whatever y value I pick, my x value is, or I can use any x value with that particular y value. So what if I picked 0 as my y value? If we plug in 0, what's going to happen for our slope? Slope of 0. So no matter what x value I'm at, when y is 0, I have a slope of 0. Which makes sense because I can't have a population if I have no people. So this function would be useless. What if I pick 1? Six. So a fairly steep slope. And you don't have to go all the way to 10. That's, again, we just need the general picture of this. What if we do 2? We get 10, we'd get an even steeper slope. I'm going to make sure this is coming out the way I thought this would be helpful, so I'm trying something new this year with this part, but I feel like it's not coming out the way I want it to. Maybe k is more important than I thought, so we can't leave it out. I left out k because I thought it would be simpler for us to graph, but I feel like this is not coming out to the logistic. No, it will. It just won't be as flat as I wanted for the good picture. So it is steeper at 2. I'm only going to go that far. If we do 3, we'll get an even steeper slope. 3 times 4 is 12, so even steeper. And then what do we get when we plug in 4? Again. We get 12 again. What happens when we plug in 5? We get 10 again. It starts flattening out again. What about when we plug in 6? Flattening out even more. And what happens when we plug in 7? We get back to 0. We get back to... So with this particular equation that we plugged in, what's the most we could be? What's our limit? When would our graph not be able to? Our graph will look something like this. Although again, these were super steep. Doesn't look quite as nice as I had wanted it to originally. What's the most our population can be? 7. So we call this number here M, the carrying capacity. And mathematically, if they asked me to find the limit as t approaches infinity of the population, that would also be my limit. That's the most my population can be. I'm limited. And, you know, they'd have to do research and actually find this equation. But if you found this equation by studying a population, we would be limited to a certain number. And then P is the population value itself. It's the Y value. So if we were to go solve this differential equation, it would look like that. This is not something you have to memorize, not something we'll make a note card for. Still good to know it exists and that you could find it if you really wanted to, but on the AP test, they will not make you solve for this.
What if you need it? Will they just give it to you? Or will you not need it at all?
They will not ask a question where you need it, or they should not.
They tell you what they're giving you.
They give me a general outline, and then I've gone through many of the tests that I have access to get a more specific picture. And I've also talked to other AP teachers to try and get a more specific picture.
And they say you're not going to have to use the logistic equation.
Yes. So I could be wrong. I mean, there is always that possibility that I am misinformed, but as far as I know, through all the research I have done, you will not have to use the logistic growth equation.
Very close.
But it's still good to see.
Yeah, that is my pattern.
So most of your logistic growth equations will be involved with some sort of word problem. Most of the AP test questions are involving some sort of word problems in general anyway. But logistic growth especially would have to be asked in word problem form.
Calculation of P of X.
So as Ben was saying, growth rate of the population P of bears in a newly established wildlife preserve is modeled by the differential equation dp dt equals 0.008 p times 100 minus p.
P is measured in years.
So our first question is, what is the limit as t approaches infinity of p of t? This will be either a very difficult question for you or a very easy question for you. It's one of those where you just have to remember the information, and if you don't remember that information, there's no way you're getting it right. But we just talked about what number in this differential equation represents the limiting number on the population. So which number represented the limiting factor on our population? 100. 100 was our limiting factor. And that's, again, something you either recognize or you don't. You have to remember it from, right now it's easy to remember because we just talked about it. We'll try and review it again when we get to closer to the AP test, but it's something you just need to remember, hey, this is, and they also call it the carrying capacity. They'll either call it the limit or the carrying capacity. They might state it either way. Yes, that is a good guess. When is the population growing the fastest?
I think it's only 0.8% of Americans.
So we have to think back to something we've learned before. It's asking us when our population is growing the fastest. What do we call finding something that's the fastest or the greatest or the least or the slowest? What do we mean when we're talking about the biggest values? Yes, maximums. I was trying to think of very many different ways to say that without actually saying the word extrema or maximum.
Oh, hey, that was what I was looking for, extrema.
Oh. So when is the population growing the fastest? So what did we have to do to find maximum? Take the derivative, set it equal to 0. Now it said when is the population growing the fastest, not when is the population at a maximum. It wants to know when are we getting bigger? What's the biggest point we're getting bigger at? Okay, so we actually do still need to take the derivative because it wants to know when the derivative is at a maximum. And there's only one word that tells you that, and that's the word growing. We want to know when it's growing at the fastest. So for B, we're going to take our equation and we are going to differentiate. We could do product rule, or we could distribute in and do power rule. Do you have a preference?
I'm going to take that as a no.
I think I heard someone whisper this. So we're going with distribute. I don't know who it was, but
You just want it, so you just heard it.
I think it's the easier way, but that's my personal opinion. Maybe it's not the easiest way for you. So 0.008p times 100. Move our decimal 2 places to the right, so 0.8p minus 0.08p squared. So now we want the second derivative. The second derivative is d squared p over dt squared. It would be 0.8 minus, and we're differentiating, not integrating. We've been doing so much integration lately. Make sure you're doing power rule and not anti-power rule. 1 times 0.8 is 0.8. Derivative of p is 1. And then it would be 1/6.
Yeah, P.
And we're setting this equal to 0. Calculator. Okay, good. Whew. I was really worried I was doing something wrong because I was like, how is this going to turn into the number I know it should be? Okay. So how do we solve for p?
Add, then divide.
Add, then divide. So we'd have 0.8 equals 0.016p. And when you divide, you get p equals 50. Okay. How does that relate to our carrying capacity? It's half the carrying capacity. If we're growing the fastest, we're growing and getting bigger and bigger until we hit the halfway point, and that's where our slopes started to, opposite of steepen, decline. That's a big one. Our slopes started to decline. So it makes sense. If you have a maximum number of bears, 50, and then they're trying to reach that capacity of 100, you're going to start slowing down the growth rate, either because you're running out of food, so can't have as many babies at the same time, or things like that. You know, there's limiting. So that's always the case. We are always growing the fastest. When our carrying capacity is at half, so when m is divided by 2. So again, if that's something you can remember on the AP test, it might save you some time. Otherwise, you could go through and take the derivative and solve, but it would still give you that half amount. And then part C, I have to scroll back up to it really quick to read it. What is the rate of change of the population when it is growing the fastest? In other words, how many cubs are they having per year when our population is getting bigger the quickest? Or maybe another limiting factor is there's not enough mates. There's more males than females or something, so they can't, there are more females than males.
Probably.
I don't know anything about bear biology, so I don't know which one it would be.
Females have the cubs.
So does everyone have this question down before I scroll back down so we can solve it? Yeah. So this one, they actually want to know the rate of change. What do we mean by rate of change? What is that a word for? The slope or derivative. Remember, derivative has like 5 billion words they're going to use to represent derivative, rate of change.
We're
slope,
taking the
I don't know.
derivative of the second
Okay.
derivative.
No, they want to know what the actual rate of change is when the population was growing the fastest. We already know the when. It was when we had 50 bears. So if they want to know how it's changing, we're just going to take our derivative and plug in 50. This will tell me how many bears they're having during the time when they had 50 bears, when they had the maximum change in population. You know, when they have 2 bears, you're only going to get so many cubs. Then if you have 10 bears, you're going to get a lot more cubs. If you have 20 bears, you're going to get a lot more cubs per year. Until we hit that limiting part that starts declining how many cubs you have per year. So if we plug this in, what do we get? 20. So 20, the population is changing by 20 bears per year when our population is at 50. If our population was at 10, it's changing by a different amount. And that's all they'd really ask on logistic growth. Those are the only kinds of questions they'd ask. Logistic growth is again one of those details that can get you some of those extra points. So our homework assignment is page 333, 55 through 58, and page 373, 23 through 26. It's only 4 problems each.
That's like,
Oh no, 8 problems.
Last homework was 3, so this is 3 days worth of
Those
homework.
3 problems took like an hour each.
Yep, so I think let's turn this in on next Wednesday.
I like how Ben has to calculate.